Hello, do you hear me? Okay, great. Give us a minute and we're gonna start. Oh, and right now I don't see you. Like, it's so shiny up here. Yeah.
Login accepted.
Okay, and this is it. Give us a second for the late joiners to come in, and we're gonna start. In the meantime, how are you enjoying the conference so far? Is it good? Yes, I thought so. Like, I enjoyed the few presentations as well in the morning. Okay, so I think that's it. So, hello everybody. Welcome to my presentation entitled How I Learned to Stop Worrying and Love the Distributed Transactions. Or, in different words, how to work with distributed systems and not to go insane. This presentation is loosely connected to the anti-war satire from 1964, called Dr. Strangelove, This Guy, or How I Learned to Stop Worrying and Love the Bomb. The movie is available on Netflix if somebody is interested after the presentation. But first, a few words about me. My name is Radosław Maziarka. I work as a solution architect and engineering manager. Currently as a consultant and trainer for Polish product companies and software houses. I specialize in domain-driven design and product thinking techniques that aim to deliver long-lasting products. I originate from .NET community, so Azure is my first cloud of choice. I encourage you to follow me on social media, where I share interesting materials and insights about our industry, about technology and engineering practices. And this presentation, materials from this presentation, slides are available at my website, on my website at radekmaziarka.pl, Love the Distributed Transactions. The QR code will be available after the presentation in the end. Okay, let's go back to our story. We, as we're all sitting here, we are building a system, an e-commerce system, but not a typical e-commerce system. We are building government's order management system. We all are sitting here as engineers and managers. We are building we are building a system where government officials can order different pieces of equipment, like from smaller tools to a bigger machinery like helicopters, submarines, and planes. Officials order a particular piece of equipment and suppliers deliver it. At first, we, as a whole, we delivered a simple modular monolith. It was there are a few modules there, but there is a single database. And because of that, where we are performing an operation, there is an opportunity, there is a chance to have a transaction across the modules. So the single transaction can span across different modules. And it turned out that our solution brought a lot of value to our customers. The business was very satisfied with the system that we delivered, and it saved them a lot of time. And so it was pretty successful for us engineers and architects. But as you can see in this room, like, there are plenty of us, and it's really hard to develop a single system, a single service with such a group. So we decided that we want to split our solution, and at first separate the shipment module into a new service. So, for example, when a client wants to fulfill an order, we send a request from orders service to the shipment service to start delivering it. On top of that, we don't want to build everything from scratch. We want to use existing capabilities that are available on the market. So we decided to use an external payment provider. So when the client, when the boat is dispatched and is going to the client, we send a request to this payment provider to carry out payment to our suppliers for the boat that they built for us. What is really interesting, what was really interesting during this split of microservice, during usage of this external service, is that it made almost no change in the code after this decomposition. That's the code from C#. That's the C# code. And as you can see, the only change after splitting our service is this word await here. So what we do is instead of doing some operation in our memory, in our process, we send a request to external service. But in the business code that we see here, there's almost no change. And of course, as we are professionals, we have tests in place, and these tests are positive. Yeah? As you can see in the above code, we mock communication to the external service. We said that if there is a request to external service, this payment service, the payment ID should be returned. Then we made a call to the order service. Let's establish that the shipment is delivered, and we should get a payment ID. Yeah. So tests are positive. Everything seems to be great. So what do we do when all tests are positive? Drinking coffee. But then after that? Yeah, the deployment to the production. Yeah, so like all tests are positive. So what do we do? Yeah, oh my God, too much clicks. Yeah, and yeah, so we just release it to the production. Great, yeah, great success. And what do you think that happened after that, after the deployment? Yeah, I spoiled it somehow, unfortunately. And unfortunately it exploded. The whole platform became unoperational. There are no functionalities that are working correctly after the deployment. Now I have a question for you. Who had a similar situation when all tests were passing, but after the deployment the system became unoperational, there were crashes, there was some miscommunication across the system? Yeah, I see a lot of raised hands, so it's not an atypical situation, so it's happened also to us as attendees of this story. So right now we need to ask ourselves, what problems have we experienced? Because we are continuously notified that something is not working as expected. We are invited to some unpleasant meetings and questions about the issues inside the system. Most of all, it turned out that messages get lost or they come in a different order. Like the customer ordered a helicopter, but the message did not reach the shipment service. So the client is waiting for the submarine that is not going to arrive soon. Or the message about the helicopter has arrived after the message that the helicopter was dispatched. And we only show the last message. So client is thinking that the helicopter is flying to them, but it was the helicopter is already there. There is another issue with the submarine. We do think twice. We send a message to pay for a boat. And the message was processed in the payment service, but the message did not reach, the return message did not reach us. So what did we do in that situation? We repeated the communication, and we got the information that it's going great. And when do you think we found out about the previous payment? Immediately? Of course not. We haven't found about it. Our business found out about it when they checked the books after the whole month. And it turned out that we are $10 million in red. Then there is another problem. When one component fails, everything fails. The customer wanted to confirm the order. And they couldn't, because in the same time, we tried to send a message to the shipment service. But the shipment service became unoperational only for a while. And because of that, we returned the information to the client that they can't confirm the order. And the client asked us, why do I care? Like, it's a completely different thing. Like I want to do my job. But they can't, because we coupled everything with everything. So when one part is not working, the whole system becomes unoperational. And finally, when something goes wrong, we have an undefined state. If the message is not returned from the payments, we have an invalid state in the order service. And we show this invalid state to the client, and they react to this invalid state, creating even a bigger mess. So what has actually occurred here is, without noticing, we introduced distributed transactions to the system. We have divided our business operation into smaller chunks, and the system becomes operational only after system is successful only after all of these operations. So system is eventually consistent. It have a defined state, a successful state, only when all transactions are successful. Unfortunately, because of our problems, it turns out that the system is eventually inconsistent. So it won't become consistent after some time. So why all of this happened? What do you think? Unfortunately, we were invited. We were invited by the horsemen of the apocalypse. And in the information systems, they are called 8 fallacies of distributed computing. These fallacies were described in 1994 by employees of Sun Microsystems, currently part of the Oracle. These fallacies present typical but false assumptions that are adopted by the developers of distributed systems. So let's go through them briefly to understand where the problem is. The first assumption is that the network is reliable, but it's not reliable. In the networks, routing nodes may not work, or the recipients may not work. And because of that, we will lose the message, or the return message will not reach our service. The second fallacy is that the latency is 0. Unfortunately, going through the network takes some time. The particular message can be rerouted by different nodes, and because of that, the message can arrive later than we would expect. Unfortunately, it happened to us with the submarine. So we sent message A and B, but message B, then A was received. Another problem is that another problem that we assume is that the bandwidth is infinite. But there is always some pain threshold to the network or to our recipient. If we send too many messages, we can saturate all the network and crash the recipient or the network. Another fallacy is that the network is secure. But the truth is that there are whole packs of automatic scanners that scans continuously the network for exploits. And because of that, we need to secure our infrastructure. And because of that, it can lead to some problems, some crashes inside our systems. For example, who has this situation that updating an SSL certificate crashed the whole website? I see some raised hands, so it's not an uncommon problem. Similar to this situation, there is a fallacy that topology doesn't change. And it's not true, because the service can change the address. There can be some proxy in between. Yesterday, we sent a message to a particular address, and it was accepted. Today, we tried the same, and the message was accepted, or was rejected, or got lost. All of this can happen because we assume that there is only one administrator. It turns out that there are usually multiple different roles that oversees the configuration, like the product team, but also SRE team, the security team. Even the customer service sometimes can change some configuration flags. Once my team had a situation that the SRE team updated a load balancer, and it crashed the load balancer for 1 minute. But it started to working operational after this 1 minute, so we haven't noticed that after we got some issues raised by customer service. The following false assumption is that the transport cost is 0. It's not strictly connected to our presentation, but it is wise to consider this cost in our overall architecture. Ask people from AWS about the egress cost, and you will get the immediate answer. And last but not least fallacy is that the network is homogeneous. The truth is that the network protocols are very distinct. gRPC, SOAP, and the rest constitute typical problems. But we, as the industry, we cannot even agree on the date format of the date format in JSON. So one team can send date as SIO, and the second will only accept messages, will only accept dates as Unix format. And even though the message is completely correct from the semantic reasons, it can be still rejected. So, like, in having all that in mind, we need to consider what should we do. Like, we cannot afford problems like that the message is lost or we process it twice, because it creates quite a big problem for our system. Fortunately, we have a lot of competent architects and engineers in this room. Together, we worked out a plan. A plan called 5 Steps to a Better System. For our system to be stable and country to be proud of us. The first step is least obvious, but let's do it anyway. Accept the situation. It's easy to convince ourselves that it's someone else's problem. That is scale of Google. Like, it will not occur in our system. Of course not. Wrong. 8 fallacies of distributed computing work just like a gravity. We cannot conquer a gravity. We can only adapt to its law. The same applies to our situation. We cannot combat 8 fallacies of distributed computing. We need to adapt our system to its law to understand when some problems can occur and solve them in advance. To do it, it is worth breaking down our problems into smaller ones. So we can ask ourselves, what problems should we solve? We got a straightforward information from our business that paying twice for a submarine is not acceptable. But what are we able to accept? Yeah, maybe there are some problems that we could live on with. So, for example, not sending a notification message about the status of the delivery. Yeah, maybe we could live with this. And lastly, how soon should we fix the problem? Maybe not all problems need the immediate response. Maybe we can solve the particular problems after a while, after manually not being oh my God, yes, solve this particular problem after a couple of hours manually, and it won't be such a problem for us. In order to answer these questions, we need some supporting materials. And just like on a field mission, we have instructions. As developers and engineers, and as engineers and architects, we have architectural drivers. These architectural drivers is a set of parameters that frame our solution. We focus on a particular aspects of our domain and omit the rest. And these architectural drivers steer the solution in a certain direction. We move on with building the solution, and these architectural drivers informs us if we are not drifting away from our goal. And these architectural drivers are context-dependent. We cannot copy them from one system to another, because the environment is different, the circumstances are different, and we need to adapt to the situation where we are. So together with our business, we discussed and established some compromises. We decided that we should focus on reliability, that we shouldn't process the message twice or lose them in action. Our system should be secure, but at the same time observable. So if there is some problem, we should know about it in advance before our client contacts us. But at the same time, we can't optimize all the parameters of our system. So we decided that we should less focus on the performance of the system, so it won't be as performing as it could be. New features will be added slowly, because we need to be sure that the reliability is in place, all the criteria are in place. And some of the orders on atypical orders will need to be placed outside of the system until we will create this functionality in the system. So right now, once we know which areas need the more sophisticated solutions, more sophisticated patterns, we can move on to the second step and change the communication model. So both with life and in systems, we cannot rely on direct communication from everything to everything. Our plans fall like domino. The same applies to the distributed systems. In distributed system, it's called temporal coupling. So as a part of the business operation, we contact to the other services in our system. When one service is unoperational, the whole system becomes similar. We had this problem when clients tried to confirm the order, but they couldn't because of the connection. To deal with this, we need to add some autonomy to the system. And it's done by implementing asynchronous communication. So we give services the autonomy to handle a particular operation in their own time. So when we send a message for example, from orders to shipment, the recipient, the shipment service may experience some problems, but they can get this message and handle it in their own time. This way, we solve two particular problems. First, by introducing asynchronous command, we solve, for example, this problem about confirming the order. So first, the client confirms the order, and they get the immediate response from us. After that, we send a request by message to the shipment service. And it's not done synchronously, it's done asynchronously. So the client is not blocked to wait for a response from a shipment service. But there is another problem, temporal coupling when querying, when asking, for example, about the status of the delivery. We can also solve this by asynchronous communication using asynchronous events. So So when the shipment, when the helicopter is dispatched, we send an event, shipment sent. And based on this event, orders can build an information about the status of the order. Then, when the client, when the client asks about the order status, we have all the information in the order service, so we respond them. This information immediately. This is the implementation on Martin Fowler's rule: tell, don't ask. So we inform external services with the information, so we avoid excessive question in advance. Our situation after second step is that we have asynchronous communication where we need to have autonomy in our system. However, regardless of whether we have asynchronous or asynchronous communication, it's good to have a reliable communication. So let's take a step forward and ensure that communication works. No one wants to work with the equipment that is not working correctly. No one wants to work with systems where communication is not operational. And it actually seems that there are a couple of places where the communication may break. So first place is that the first situation is that the message can be labeled to be sent, but won't be sent after all because of the problems with queue. The second problem is that the same message can be sent twice or more. And the third possibility is here that the message will be rejected by some reasons from the recipient, from our shipment service. So let's tackle the situation and take the first. As a part of the order service, we can implement outbox pattern. Based on the confirmation scenario, first we order information about operational data and communication data transactionally in the database. We have an outbox table to store information about the communication to the external systems. Then there is another component, publisher, that gets all the messages to be sent from the database and sends it to the queue. By implementing outbox pattern, we are certain that we will save all the important information about the order, but also communication in the database. And where there are some problems with queue, we can repeat the communication after a while. In the above slide, the handler and publishers are two different components, but they usually sit in the same service. Subsequently, the problem of processing the message twice. We can solve this problem by using idempotent receiver and inbox pattern. So when we send a message about the delivery of a helicopter, we add idempotency keys, a key that is usually called idempotency key. So it's the unique identifier of the particular message, of the particular communication with the external systems. Then our recipient, the shipment service, can check whether it hasn't already processed a particular message. The recipient usually has a store called inbox, where they store all the messages that are processed. And if the message was or is already processed, the message is rejected. The last problem here is that the recipient will not process the message. We can implement the dead letter queue. So when the message is rejected, it goes back to the queue, to the queue named dead letter queue. And then we can monitor this queue for the messages that were rejected and act on them. So we can, for example, inform the business, we can repeat the communication in the particular system, adopt the rejection, and handle them in the reliable manner. And right now I have a question for you. Please raise your hands. Who among you uses that letter Q? Yeah, I see a lot of hands. And who please, sorry, please keep your hands up. And who among you have processes and monitoring around that letter Q to handle problems? Yeah, I see that like about the half of people like in this room lowered their hands. So it's not enough to have only the letter Q, because we need active monitoring and processes around them to solve particular problems. But we adapted these processes, we introduced monitoring, and after the third step, we have inbox and outbox pattern at two sides of the communication. Messages are processed reliably only once using the idempotency key, and when there is some problem in the recipient, message gets to the letter Q, and it's handled by different processes. However, this may not be enough to handle distributed transactions and get the information about the status of the transactions. So as the fourth step, we decided to manage transactions. We should know what happens to others when we delegate them duties, even though we are not performing these duties ourselves. Looking at our system, how do we know what is the status of the transaction? What is the status of the communication here? If there are some problems, for example, like how long should we wait? How should we react to the problems that are occurring in the external system? To manage these kind of problems, these distributed transactions accordingly, we can use the Saga pattern described in 1987. The Saga pattern describes that we divide the business process into independent business transactions. So the local transaction meets the business needs in the particular service, and then we inform from a single service another service about the state of our transaction. So in our situation here, we confirm an order, then the information is sent to the shipment to start building a particular equipment, for example, this helicopter. Then we get the information that the helicopter is dispatched. Then we send an order to pay for this helicopter. We get the information that the helicopter was paid. So we send information to our client that the helicopter was paid, and they can wait for a helicopter in a particular location. Together, these transactions form a saga. If there is some problem within this communication, if the transaction fails, we can still fix the state, compensate for it. For more complex distributed transactions, we store operational data, so in our context, orders data, and the state of the communication and transactions separately. So for example, we will have orders data for operational data and order Saga data for the state of the communication of the transaction between the services. So the helicopter was dispatched, and we sent information, and we sent a request to pay for a helicopter. We have all the information stored in our Saga, and because of that, we know immediately what is the status of the communication. On the other hand, we have prepared ourselves for various contingencies that come when there are problems. So our Saga can compensate for a business transaction. So when we get information about payment failed due to lack of funds, we send information to the shipment service to stop processing shipment, because we are currently not able to pay for that. After the fourth step, we manage our distributed transaction in a secure and observable manner. If there are some problems, we know how to act on them and how to observe them. At the very end, we can prepare ourselves even better for potential problems of distributed systems. So let's take the ultimate step and handle errors in advance. So as quote says, you've got to be in a position for luck to happen. So we need to prepare for luck to happen and not to wish that the luck happen itself. Because it's the undeniable fact that it won't always work. Because there will be some problems in communication. Communication can get lost, services can go down. To handle these challenges, we can prepare ourselves even better with 3 additional patterns. First, the retry pattern. So when the message is not processed, we can repeat our communication. But it's not wise to do it immediately because we can create a retry storm and break the recipient. So it's better, so instead we can use more advanced patterns like exponential backoff or jitter to add some time for the recipient to react. After some amount of time, we can even contact the external service synchronously to check if the service is working. If the communication isn't completely operational, we can use circuit breaker. At some point, we open the circuit to external service, and we stop communication for a defined amount of time. We can even show some information to the client that the external service is not operational, so the continuation of the process is stopped, or they can't create new orders because of that. In order not to completely miss out the opportunity, we can use caching mechanism. So we store information about the state of the process in the caching mechanism. So when the client is calling us for a data, we know how to react. You react to it based on the information that we store in our system. After the last step, we applied these patterns in the places where it brought us value, where it helped us solve particular problems. So after 5 steps, how far have we flown with our plane? What results have we achieved with our system? Above all, we have introduced reliable processes into our system. If the message about the delivery of the helicopter got lost, we know how to act on that. If we ask to pay twice for the submarine, nothing happens. We figured out the different scenarios, different problems, and created the solution in advance. Next, we have more accurate observability in our system. We don't need to read 1,000 lines of logs. We have the state of the system directly in front of us. For example, as the state of Saga. So like in this movie, where is my helicopter, dude? There it is. It's flying to you. We assumed that something will fail, and we created a protective net in our system. Based on that, we can scale our solution. We have developed practices that allows us to add new services without much problems. So for example, when we want to add invoicing processing in our systems, we know how to do it. Some problems we know how to solve, some how to mitigate. But nothing in the production will scare us, will surprise us. And the most important of all of this is that we will not go insane with a distributed system in production. The bomb doesn't explode. The helicopters are flying. Submarines are arriving. From developers' perspective, we sleep soundly. We are not bothered with some ad hoc meetings. We can focus on writing code. From architect's perspective, we know how to plan building even the bigger system, adding even more sophisticated functionality. It gives you peace of mind. And I wish you this peace of mind while working with distributed systems. To wrap up, let me share one last insight with you. All of these problems happened because we decided to split out our system. Therefore, the most important message here, the most important rule of distributed system is not to create them in the first place. But when you do, remember about the problems that follow. It was a presentation entitled How I Learned to Stop Worrying and Love the Distributed Transactions. In the end of this presentation, I have 4 major takeaways for you. Remember the 8 fallacies of distributed computing. They act just like gravity. You need to adapt to them, not to combat them. Then evaluate where is it worth using more complex patterns. There are places that you can live with a failure. But if not, use the patterns described in this presentation. Third, use asynchronous communication where possible. At some places you can use such patterns, such asynchronous communication. But in most places you can, and therefore you will avoid problems with distributed computing, with distributed services connections one another. And fourth is manage distributed transactions. They won't manage themselves. You need some place to manage communication between different services. Here are some books that I can recommend you to deepen the knowledge about the distributed system. First, Enterprise Integration Patterns. The book comes from the beginning of our century. It consists of multiple patterns of out-of-the-process communication, and currently some of these patterns are already included in the libraries or services that you use on a daily basis. Second book is called Microservices Patterns by Chris Ricardson. It's a very definition, is a very well-written description of how to build microservices, and also especially around the Saga pattern. And finally, Monolith to Microservices book from Sam Newman on different various patterns, how to split your system into smaller parts. If you'd be interested in a distillation of this knowledge, I can recommend you my tech lead training. I teach on how to use architectural drivers to build distributed systems, and a lot on top of that, both in theory and in practice. If you are interested in the materials from this presentation, they are available at radekmaziarka.pl, Love the Distributed Transaction. You can catch me on LinkedIn, and thanks for being here. And if you have any question, you can approach me at any moment during the conference. See you.